regression analysis. So we know that we go for linear regression. If x, the variable x and the variable y are linearly correlated. In other words, there is a linear relationship between them. So if we take the value of r is close to 1 or -1. So we have two different samples here, one where x and y are related to each other in a negative manner. In other words, as x increases, y decreases. So the first case is negative correlation. The other case is positive correlation. So negative correlation, the value of r is expected to be between -1 and 0. Where r is simply the linear correlation coefficient. With positive correlation, the value of r is going to be between 0 and 1. Again, r is simply the linear correlation coefficient, and we talked about this in the previous video. So now we have a sample, we have an idea as to what the data is going to look like. And we see a linear pattern in our sample, and our objective is to fit a model or come up with a model that would describe the relationship. So the goal here is to create a model to describe the relationship. So if you look at this, you can say, well, could I describe this mathematical expression as, say, y equals 2x² plus 3x plus 1? Well, we cannot, because that is actually a quadratic equation. So that expression would work if we have a nonlinear U-shaped relation. In other words, a parabola. So the expression that we choose has to be meaningful. So what expression would define a line? Because what we see here is a linear correlation, a line-like correlation. So we know that if we want to represent a line is represented using the equation y equals mx plus b. You can either call it ax plus b or mx plus b. There are other notations also. It is a matter of choice. So a here is the slope term, and b is the y-intercept term. So we know that we can represent a linear relationship if we can come up with a line. And in order to come up with this line, we need to know the values of a and b, the slope and y-intercept. So So how do we come up with A and B? This is where statistics comes into play, and this is what we call regression analysis, or least squares regression analysis. So we need to find the value of A and B. If we find the value of A and B, then we can come up with the equation of the line that describes the relationship between X and Y. So we call it a least squares regression because of the theoretical derivation that is behind the process of finding A and B. We also call the line as line of best fit. The reason being, so if you consider the two samples that we have, I can draw infinitely many lines through the data. For instance, I'm going to take the one that has positive correlation. So I could draw a line of that sort. I could draw a line of that sort. I could draw a line that goes there. And if I asked you, which line do you think that best represents the sample, we will most certainly pick the one that's in the middle, because that sort of goes through the data. It represents the data really well. This one, the one below, is way off. That one, the one above, is also way off. So the one that's going through the middle, through all data points, is the line of best fit. So the reason why we call it the line of best fit is because we are trying to find the line that best represents the data. We call it least squares regression because of the mathematical process that is involved in finding the values of A and B. So the line of best fit, if we have to come up with it using the data, then we have to find the values of A and B. So in the negative correlation case, a good line should be of that sort. So the nice thing here is you don't have to worry about which would be the line that's going to best represent the data. Whatever line that you get at the end of the least squares process is guaranteed to be the line of best fit for a given paired sample of X and Y data points. So now we have to come up with a way to find A and B. I'm not going to get into the derivation of A and B. It's not needed for this class, but I will show you the underlying process in finding the values of A and B. So we have this line that is going through the data. So what we're trying to do is to find a model, a line, where we would be computing the values of A and B. The value of slope and the value of the intercept computed using the sample. So I put a hat on top of each variable except x, because the hat indicates that those values are computed from the sample. In other words, they are statistics. So A hat and B hat are estimated So the original A and B that we were looking for, now we have computed it using a sample, and that is what we have here. Now, if I use this particular model that I obtained from the sample, I'm not going to get the exact Y value that I had in the original data. So the value that I obtain from the model is what we call the fitted value. The original value in the sample is the actual value. So before I get into more details, let me just show you a good example. Consider so if you look at that data that I just created, the value of R is going to be 1. It is a perfect linear relationship, no variability at all, in contrast to the figure that is on the top left corner. So and I know the equation that would describe the line. So the model here is simply 2 times x. The y-intercept is simply 0. So the actual values of y are 2, 4, 6, and 8. If I plug in x, in the equation y hat equals 2x, I would get the fitted values. So if I use the model, I plug in 1 into x, I'm going to get 2. Plug in 2 into x, I'll get 4. In a similar manner, I'll get 6 and 8. What is the big deal about this here? Well, note the actual and fitted values are the same. In other words, what we call as a residual, y, the actual value, minus the fitted value is 0. And you may say, well, why do we care about the residual? Well, the example that I started with is the perfect case. In reality, we will never get a scenario like the one we have on the bottom right corner. Because if we have a perfect relationship between x and y, I know what equation to use. I don't need statistics. I don't need least squares regression. I could just write the equation using algebra. So in reality, in practice, the residuals for each observation is not going to be 0. So this is because of the fact the relationship is perfectly linear. So in cases where the data is not perfectly linear, but we can explain the relationship using data points, such as the one here, we can compute the residual. So what is the residual? Mind you, residual is simply the value of y that you get when you plug in the value of x in the model. In other words, we are talking about the fitted value. So as an example, let me pick a point here. I'm just making sure that the points look far away from each other. Okay. So let's pick that point from the sample. I'll just call, x6. It's the sixth or seventh observation that I see. So x7. So the actual value here is x7, y7. But the fitted value corresponding to x7, y7, in other words, whatever value that we get using the model is the value that we see right there. Clearly, the actual value and the value that is given by the line are not one and the same. In other words, there is a difference between those two values, actual minus fitted. So that is what we call a residual. Another case, let's just take a simpler one. The observation x3. So that point is x3 and the corresponding y value is y3. So the actual value is x3, y3. But if I take the value of x3 and if I plugged it in the model that I fit, the line of best fit, that point is going to be on the line. And it is not going to match exactly the value of y in the sample. So there is a tiny difference, and that tiny difference is also the residual. So the goal is, if I keep on reducing the residuals between the point and the line that I want, then eventually I'm going to get the line of best fit. So one may say, let me just add up all the residuals for a line and find the line that gives me the smallest sum. Then I would minimize the error. The residuals are simply error values, the error that you have between the actual value and the fitted value. So you may say, well, let me sum all the error values that I have and I'll find the best line that minimizes this error. But unfortunately, if we sum the residuals in a data set, it will be 0. Mathematically, it will end up being 0, and we can't do anything about it. So what we do, we take the sum of squared residuals. So for each observation, and it's the sample size, I am going to have an actual value that is in the sample, the fitted value, so the fitted model is going to use different values of A and B. So we have the actual value and the fitted value. And what we're trying to do is minimize the sum of all the squares. In other words, we're going to minimize the error. So in simple terms, what I've written here is the error, total error in computing the fitted value. So the line of best fit minimizes the sum of squared residuals, which is why we call the line of best fit as the least squares regression line. So the line of best fit is the one that is going to have the least squared residual values. Hence the name least squares regression, line of best fit, and so on. So our objective is to use the method and come up with a model. Unfortunately, I'm going to give you the values of A and B that would actually minimize and give you the line, minimize the sum of squared residuals and give you the line of best fit. So here is the expression. So we compute A hat and B hat using the sample. So the value of A hat is simply the value of the correlation coefficient multiplied by the standard deviation of Y divided by the standard deviation of X. And B hat is simply Y bar minus the value of A hat that we computed multiplied by X bar. So here X bar is the sample mean for X, Y bar is the sample mean for Y, A hat, well, let me write that later. S sub X is the sample standard deviation. Sy is the sample standard deviation for the sample Y. And A hat is the estimator for slope. And B hat is the estimator for y-intercept. So if we have a sample, we are trying to find the line of best fit. And how do we find the line of best fit? We simply find the values of A hat and B hat. And what do we need to find the values of A hat and B hat? We need the value of the linear correlation coefficient. The standard deviation, sample standard deviation of Y, sample standard deviation of X, and the sample means for X and Y. So we are going to revisit the unhealthy commute example where we had the commute time versus the Gallup Health-Based Wellbeing Index composite score. And we determine the explanatory and response variable. The response variable is what I called as the G score, the Y variable, and the X variable is the explanatory variable, which is the commute time. And we obtained a scatter diagram. The scatter diagram did look like a line, so there was a linear relationship. So we went back and we used the formula for linear regression, linear correlation coefficient, and we ended up getting the value of R and the sample statistics also. The value of the mean happened to be 43.86 for sample X. The value of the mean for sample Y, or the G-score, was 66.93. The standard deviation for X was 34.98, and the standard deviation for Y was 1.709. And the value of R was simply negative 0.9810. So from previous calculations, we have the mean, we have the standard deviation. We determined the value of the linear correlation coefficient as negative 0.9810. Does a linear relationship exist between the commute time and the well-being index score, which is the G score? Absolutely, we know that. The goal is to come up with the line of best fit now. So what is the line of best fit? The line of best fit is simply A hat x plus B hat. We know the formula for A hat, which is the value of R multiplied by the standard deviation of Y divided by the standard deviation. So negative 0.9810 times 1.709 divided by 34.98. We need the calculator. And that gives us a value of negative 0.0479. The value of B hat is simply Y bar minus A hat times X bar. So we have 66.93 minus 0.0479. That is the computed value of A hat, and multiply that by 43.86. And we end up getting a value of 69.03. So the fitted model here Y hat equals the value of A hat that we determined, which happened to be the value of A happens to be negative 0.0479. So Y hat is equal to negative 0.0479 times X plus the value of B hat, which is 69.03. So that is the fitted model that would explain the relationship between the well-being index score and the commute time. And of course, it is worthwhile to mention that this is obtained using the data that we observed. Great. Now, we have to get into advanced mathematics to make it a point that whatever line that we found will have the lowest sum of squared error. But, in this class, all we have to do is understand the concept of actual value, fitted value, and this residual or sum of squared residual error. So I'm going to show you how to find the the fitted values. So we have the chart here. So let me just copy that. Happened. Copy. Weird. Okay. 20, 20. Okay. So for each of the x values, we have the actual y values. So what we have here in the given table would be the actual values. Now I'm going to write the fitted values . So I'll put it in a teal color. So how do we find those fitted values? Mind you, fitted values are values that are given by the model. So I'm going to enter the x values. So 5, 15, 25, 35, 50, 72, and 105. And I'm going to use an equation to compute the fitted values. And what would that equation be? That equation is our fitted model. So negative 0.0479 multiplied by list 1 plus 69.03 and enter. So it automatically populates the values here. So the actual value when x was 5 was 69.2. The fitted value is 68.79. The actual was 68.3 for the next case, and we have 68.31. the next case, we have 67.83, then 67.35, 66.64, I'm going to round it, 65.58, and 64. And you can see in most cases, the fitted values are very close to the actual value. So our model is actually doing a good job. So all of my actual values are in list 1. My fitted values are in list 2. And we know that if we did L1 minus L2, we are going to end up getting the residuals. So actual L1 minus fitted L2. And I'm going to save that to list 3. And oh, I'm sorry, that's not right. I don't have the actual values in list 1. Have to enter the actual values. So I'm going to enter it in list 3. List 1 has the X values, and I apologize for that, my mistake. So I entered the actual values of Y in list 3. The fitted values, the values that we obtained from the model, are in list 2. Now, exit. So actual values, list 3, minus fitted values, list 2. And I'm going to store everything using the store key in list 4, or to list 4. So enter. Now list 4 has all the residuals because we simply computed the actual minus fitted values and saved it to list 4. If I did one last touch on list 4, the first one is the sum, mean. The second one is the sum. So you have negative 0.0047, which is approximately 0, a point that I made earlier. If we sum all the residuals, the sum of the residuals must be 0. What is the sum of squared error? The sum of squared error is 0.6771. And this is the lowest squared error that the process can find. Hence, we get the line of best fit. Now, one may ask, well, why do we need to come up with this model? If you look at the data, you have commute times from 5 all the way up to 105. What if my commute time to work is 75 minutes? So someone asked me, well, based on the model that you have, what is the predicted whose commute time is 75 minutes. Well, clearly 75 minutes is not in the chart. I can't pick it out from the chart directly, from the data that is given to me. But I do know that the model up here that we fit is a good candidate into or in explaining the relationship between X and Y. So all I have to do is take the value of 75 minutes, which is simply the X value, plug it in our line of best fit, that is our model, and I would get the well-being index score. So Y hat, when X is 75 minutes, is simply negative 0.0479 times 75 plus 69.03. And that happens to be 65.4375. That's pretty straightforward. And the key thing to notice here is to remember that the value that we find when X is equal to 75 for Y hat has to lie between X is equal to 72 and 105. So does 65.4375 lie between 72 and 105? Yes, because it is right over there. So 65.4375 would lie between 65.58 and 64. If it doesn't happen this way, then clearly you made a mistake somewhere. It has to behave in this manner. A word of caution, when predicting the way I just did, so predictions can only be done within the observed range of X values. In other words, you cannot go outside of or pick an X value bigger than 105 minutes or pick an X value below 5 minutes. And, you know, if someone says, well, my work is right next door and it just takes me a minute to go to work, what would my well-being index be? Well, you cannot use this particular model because this model is good for values, X values between 5 and 105, because that's what we observed. So height and the head circumference of a child. So a pediatrician wants to determine the relationship between the height of a child and the child's head circumference. The pediatrician is curious, so she selects 11 3-year-old children from her practice, and the data that she has here is what she had recorded. So we have the height values and the head circumference values. And part A wants to know if the pediatrician wants to use height to predict head circumference, determine which variable is explanatory and which is the response. So in the verbiage itself, you should sort of have an idea as to what the response and the explanatory variables are. So wants to use height to predict circumference. So that tells me immediately that height is X, and predicting head circumference would imply the head circumference is Y. What is another way to think about it? It's to think really logically. Now, could a person's height determine the person's head circumference, or would a person's head circumference determine the person's height? So would it be reasonable to say if I have a huge head, then I'll be really, really tall? Or would it be reasonable to say a taller person is likely to have, you know, a head that is a bit larger than a shorter person? Well, the latter sounds more reasonable to me. So you can't identify X and Y, you know, just by understanding the problem, or you can just read the question and pick it out directly from the question like I did. So in this head circumference would be the Y values. Now we want to draw a scatter diagram and come up with linear correlation coefficient and the model. So I am going to enter the X values in list 1. So let's just double check. Okay, everything looks right. So I'm going to obtain a scatter plot. So start plot. And it is the first one. And by default, the calculator chooses list 1 to be the X values and list 2 to be the Y values. So I'm going to hit graph, and I'm not going to say anything because I haven't set the window properly. So the X values are in the range of 20s. So I'm just going to go for 24 all the way up to 28. The Y values are the range of 16s and 17s. So I'll simply do 15 all the way up to 20. So if you look at that scatter diagram, you see as if there is no relationship between X and Y. In other words, it looks like a flat line. You can see a line, sort of a line, but that line is flat. X and Y are not related at all in the sense Y is not varying as X changes. So we could find the value of R to see if we are doing something wrong or if we are interpreting something wrong. So let's find the value of R and come back to see if our interpretation of the scatter diagram is actually incorrect. So we know the formula of R, it's listed over there. So we have to find the z-scores of all X values, multiply with the z-scores of all Y values, sum them all together and divide by n-1. So to do that, we need the mean for the X sample, which is height. We need the mean for the Y sample, which is head circumference. And we know how to find this. We just have to do one variable statistics. So start over to calculate. List one would have the x values, or it has the x values. So x bar is 26.45. The standard deviation for x is 1.094. And the head circumference, those values are in list 2. So start, calculate, one variable statistics of list 2. The mean is 17.32. Guess I could round it to 17.33. And the standard deviation is 0.2195. So now that we have the mean and the standard deviation, what we can do is we can find the z-scores of all the x values, the z-scores of all the y values, multiply them, then we could find the sum. So all the x values are in list 1, so second 1, minus the mean, 26.45, divided by 1.094. That would take care of the first part right here. And we have to multiply that with the y values. So y, all y values are in list 2, minus the mean of y, which is 17.33. And divide that by 0.2195. So that is the answer that I get. And whatever answer that I have, I'm just going to go ahead and store it to list 3. If I go back, I can see those values in list 3. And now I have to sum them all and divide by n-1. To do that, I'm going to press start, over to calc, one variable statistics of list 3. So the sum of all the values is 9.1199. It is in the second line. We have to divide that by 11 minus 1, because we have 11 children, and the formula says divide by n-1. 11 minus 1 would be 10. So we will have 0.9119. Now, based on what we know, that is strong positive correlation. And that answers part D. Does it have a strong positive linear correlation? Absolutely. But earlier we did the scatter diagram, and our interpretation of the scatter diagram was that, oh, there is no relation, there is a relationship, but y doesn't depend on x, because the slope is sort of 0. It looks like a flat line. It doesn't look like a line that has a slope. What are we doing here? What is our mistake? Mistake here is the way we are plotting the data. If you look at all the y values, the range of y values, it's very narrow. It's somewhere from 16.9 up to a maximum value of 17.6. And that is a narrow range. But when I set the window for y values, I set it from 15 all the way up to 20. And that is why we're not seeing a linear pattern, but the moment we calculated R, it gave us an idea that we are doing something wrong in terms of the interpretation, and we have to go back and reevaluate, and that's exactly what I'm doing. So I'm going to go from 16.8 all the way up to 17.7. And there it is. Now, is that a perfect linear relationship? No, but could I draw a line that would explain the data points? Possibly. So the data is somewhat linear, and the value of R also indicates the same. So there is a linear correlation, and it is positive. Now we just have to find the mathematical expression that would give us the linear relationship between height and head circumference. So y hat is simply a x plus b. We need to find the value of a hat and b hat. The formula for a hat is r multiplied by sy divided by sx. So we would have 0.9119, that is the value of r, multiplied by sy, which is 0.2195, divided by sx, 1.094. We end up getting 0.18296. We'll just leave it at 1829. The value of b hat is simply y bar minus the value of a hat that we found multiplied by x bar. So y bar is 17.33 minus the value of a hat that we just found, 0.1829, multiplied by x bar, which is 26.45, the average height. And that gives me a value of 12.4922. So the fitted model is y hat equals 0.1829x plus 12.49. Now, we did this entire process to come up with a linear regression model. But if you have the actual data, the calculator will make linear regression a bit easier for you. In what way? So we have already entered the x values in list 1 and y values in list 2. So all we have to do now is to press start, go over to calc, and you can see option number 4 is linreg. Linreg stands for linear regression. And you simply have to say list 1, comma, list 2, indicating that the first variable is the x list and the first list is the x variable and the second list is the y variable. And if I hit enter, you can see I get the value of a to be 0.1827, and that matches up closely with mine. And the value of b is 12.49. That matches up with the value that I have. Now, why is the slope value slightly off? It is slightly off because of rounding. I've rounded the average, I've rounded the standard deviation, and that is why it is slightly off. So if you have the X and Y values given to you, if they are provided to you in the problem, you can avoid the formulas altogether and jump directly to linreg in your calculator and get the fitted model. So now that we know that there is a linear relationship between X and Y, we made use of the data and came up with the model, which is right there. So that is the head circumference. And that is the height. I believe both of them are in centimeters. Now that we have this model, let's see if we can make a prediction. So I'm looking at this and I'm looking at the X values. I don't see 24 in the X values. And say if a parent came and asked you, well, my child, the height of my child, 3-year-old child, is 24 inches, what would the head circumference be? So what is since we fitted the model, we actually have the model expression. So what we have to do is simply take the value of 24 inches, plug it in the model, and get the value of the head circumference. So when X is 24 inches, so we have this new 3-year-old child, and the child's height is 24 inches, we want to find the corresponding head circumference. So all I have to do is plug in 0.1829 times 24 plus 12.49 in the calculator, and I'll get the answer. Which gives me 16.88. So if we go back here, between (24.5) and anything below 24, we actually don't have an observation. So earlier I mentioned about being careful about predicting a value that is within the range of data. So even though we were able to compute the value of y for x is equal to 24 inches, so you have to be cautious over here because the x equals 24 inches is outside the range of x values studied. So is it doable? Yes, but we just have to be very careful in interpreting that value. So if we changed it and said, well, what if x is 24.75 inches? And 24.75 definitely is within the range of the data because I have 24.5 here corresponds to 17.1 and 25 corresponds to 16.9. So all we have to do is plug in 24.75 and we will get the corresponding circumference. And that comes to a value, about 17.02 inches. And does it fall, or does it seem reasonable? So 25, we have a value of 16.9, 24.5, we have a value of 17.1, and 24.75 lies between 24.5 and 25. The predicted y value, 17.02 inches, falls between 17.1 and 16.9. So even though that 24 inches is reasonable, when x is 24 inches, the value of y that we found to be 16.88 inches is reasonable, we have to be careful because we did not study that specific value of height in our data. So as another example, if we plug in 24.75 inches, 24.75 certainly is in the range of the data, the x values. So I know that the corresponding head circumference will be 17.02 inches.